In this tutorial, we're going to model the rack and pinion. Here's one I modelled earlier. So we can move the rack or the pinion, and both parts move in unison. The tooth profile for the gear is based on an involute curve. This is a specific type of gear tooth profile. You can see that there's a very tight meshing of the gear teeth. This is because this particular model has no backlash. Backlash is something that we'll cover in a future tutorial. So let's have a look at remodeling this assembly. So we're going to start by creating a part. And we're going to create some base geometry, some master base geometry to start with. I sometimes need to reveal the equations tab on the left hand side. So I've just right clicked and gone in and opened. In the global variables panel, we'll enter the module of 3. We're going to add the number of teeth, and we're going to make this 32, and we'll add a pressure angle of 22 degrees. We'll add one more variable after this, which will be the tooth radius. It's less important than these first 3 factors, but the first 3 items you can see here are going to drive all of the other equations that are going to generate our tooth profile. So the reasoning for entering these global variables in the equations header is very simple. This is going to give us control over the geometry we're about to produce. The next thing we need to do is we need to add some reference geometry. We're going to put together an axis. So in axis reference geometry, we're going to select 2 planes, the top and the right plane. I'm going to use them to form the axis. The axis we'll rename. We'll call this a rotation axis. So we know in future that this is the center of the part. Let's now draw on the front plane. So we get a sketch. We're modeling on the front plane, and we're going to draw 5 circles. And this is the skeleton geometry for the basis of the gear. So we'll take the second circle and we're going to rename pitch circle. So we're basically going to create some equations to create each of the variables. So equals global variables module times global variable number of teeth. And this is exactly why we input those variables into the equations tab at the start, so that we can use them here. Let's name the next circle, the largest one, the addendum circle. And this is going to equal the pitch circle plus, so not times, plus a global variable again, module times 2. Okay, that gives us our larger diameter, the addendum circle. The next one is going to be the clearance circle. This is the limit of the tooth meshing contact. So the clearance circle again equals the pitch circle minus the module times 2. And this gives us the limit of the tooth meshing It becomes clear later. So we've got 2 more circles left. We now need to input the base circle. The base circle is going to drive the involute curve that we're going to use to form the tooth profile. So equals the pitch circle again, but this time times cosine of the global variable, which is the pressure angle. So cosine pressure angle. So the last circle represents the root circle, which is the very root of the depth of the gear, gear tooth. So this equals the pitch circle minus the module times 1.25 in this instance times 2. So 1.25 times 2. And that gives us our base geometry to form the tooth profile around. So let's just line everything up. And then we'll close this down briefly and go back into the equations tab. So close, right click on equations, manage the equations, and you can see that all 5 of these circles have now appeared with the equations and the calculations. Okay, so let's select the sketch and we're going to extrude. So we're just going to extrude by 20 mm. It's an arbitrary figure. We're going to select contours, get rid of the sketch, we don't need that. We do need the largest circle. Select the largest circle. And let's change the color because we've got a horrible grey. So let's right click, change to the body. Let's make this yellow. Okay, so now we've got something to start forming the tooth within. So let's reveal the sketch. Let's get rid of the solid just for now, just turning it off. And we're going to draw on the front plane. So we sketch on the front plane and we're going to form our involute curve. So let's put in a reference line which is going to go from the center to the base circle. And then we're going to create an array. Turn this into just construction geometry first. So a circular sketch pattern. We'll select the center point, which is the center of the rotation axis. We're going to rotate about 45 degrees and we're going to select 11 instances. And the entity is the line we've just input. So here we can see a preview and then we've got our pattern. So let's just freeze it 45 degrees. So we just put some constraining geometry so everything goes black, so it's now fully constrained. And we've got some reference geometry to start building our involute curve around. So let's do the first. Let's put a line in. This is a reference line and then one at the end. And then we're going to make these tangent to the lines we've just put in. So each of these are going to be tangent. So the first and the last. And we'll dimension these lines. And this is going to give us what we need to build our involute. So this is an arbitrary dimension. We don't care what it is at the moment. These two construction geometry lines. Right, so remember these. So 5.78, 22.19. Let's come out of the sketch, go back into the equations tab, right click, manage equations. They don't appear, so we need to flip over to dimension view and we look at the bottom, and these two dimensions have just appeared here. Here we can add an equation. So the longest length is going to be an equal, and it's going to be the base circle times pi, and then that's going to give us the circumference. We'll divide that by 8, and that will give us exactly the 45-degree circumference. So 34.95 is that circumference of the base circle at 45 degrees. For the first line, so we divided up into 10 sections. So we're going to take that circumference measurement, divide it by 10, because we've got 10 slices when we go back and look at the sketch that we've got. So that's 3.5. Okay, and the reason why we need the circumference is because we're pulling a taut piece of string away from the start point of where our involute is forming. It's going to start to make sense in a little while. We need some more reference lines. All these reference lines we're now inputting, they're going to be perpendicular to the initial geometry that we built in our pattern, circular pattern. So this is going to be dimensioned, this second line, and it's going to be double the first one, because we're double the distance away from our start point, which is the vertical line. So equals that initial sketch times 2. Sorry, that initial sketch dimension times 2. So we do this again to the next line. This is perpendicular again, or it will be. We select the 2, make them perpendicular, and then we dimension this new piece of geometry equals the initial dimension, this time with 3 times the distance, so times 3. And we're going to build this up along each of these angles. So we're just building some base geometry. Equals the initial dimension times 4 this time. The next one, remember it's perpendicular again. Perpendicular. And this one is times 5. So equals 3.5 times 5. So we're adding increments every time, and you can see there's a pattern forming which we're going to link our involute curve to. Equals 3.5 times 6. The next one is times 7. And you can see this has all been formed from the base circle. So you need to be very careful that you build this involute from the base circle and not the root circle, not the pitch circle. It always forms from the base circle. Some of these dimensions are a bit tricky to get a hold of. So 3.5 times 8. We got one more to do. The last one, here he comes, because we already have number 10. So this is 3.5 times 9. Okay, so now we need to make all these lines construction because we don't need them in any other form other than as construction geometry. And you can see the curve is going to follow this path. So just to show you, if I take like a conversion of the base circle and I highlight it, and I've taken a section of the base circle at 45 degrees. And if I go to evaluate, measure, the measurement, the arc length is exactly the same as the longest length that we input. So this is a nice little check that you can do yourself to see if you're building your involute curve properly. And if it doesn't correlate, then you know something needs to be changed. So let's get rid of that. Okay, so we need to build the involute, not using a straight line. That was wrong. Let's start again. Get rid of that. Okay, and we're going to use a spline. So we start at the vertical and link up each of these lines until we get to the last one. And we've got our involute curve. So let's make everything we don't need construction, including this line here. And then we're just going to shift it over just for now. So we delete our vertical constraint and we'll just move it around the curve because we need to build some more geometry to form the teeth cutout. So this time a vertical line to the pitch circle and then one either side. So let's mirror these around the vertical. Sorry, make them symmetrical around the vertical. And then we're going to dimension this angle. Now this angle is going to be half of the circular pitch. And this angle is 360 degrees divided by the number of teeth divided again by 2. And this will give us the width or the arc length of the tooth profile, the gap. This gives us the exact gap that we need without any backlash. So we take our involute curve and we link it to the intersection, and then we mirror our involute curve across the vertical line, and so we've got a cutout for our involute, for our tooth depth. We're going to feed down to the root circle, so let's highlight the root circle, go convert entities, and also the addendum circle. We need to link up. So let's just create some geometry there. We need one there, one line there. So we're going to mirror about the vertical line. We're going to mirror this line we just input here. Should have done that earlier. And then let's just trim some excess geometry off. So the circular pitch has given us this gap. It's told us exactly how wide this gap needs to be for this tooth profile to work. Okay, we've got everything we need now. Built our geometry, we can now make our cutout. So let's reveal our solid. Go to features, extrude cut. We can go through all, turn off the fin feature, select the contours. First, let's spin the model around. Let's reveal our checkbox for our selected contours, and we'll select this section. And we're going to go through all, and we're going to make a cut. So we've got our base tooth. Now, there's something else we need to add here before we make an array. We need to consider that tooth radius that we input earlier. So we're going to make a fillet. Let's make it 0.4 for now. And then we're going to select the base and the top just to round these corners off. We don't need to do this, but we're going to do it. And we need some control on these. So we're going to go into equations, right click, manage equations. We're going to find that 0.4 in this list that we've just input. We're going to change that. So this is going to be equal the global variable tooth radius. And that gives us the control input. Okay. We're now ready, very, very close to being ready to finishing this off. So we're going to make a circular pattern now. So about the rotation axis, let's leave this at 5 instances to begin with, but we're definitely going to rotate about 360 degrees. So we go to features, cut extrude, we select fillet. We've got a preview, and we'll say OK. Now this isn't really the gear tooth profile at the moment. We need to make some changes. So back into equations, manage equations. Let's just reveal this so that we can see. You can see it doesn't really look like a gear profile at the moment. So let's change that pattern. So equals global variable number of teeth. And we'll say yes. And we've got our finished gear or pinion. So this is a good, we've got some good geometry to now take into creating the rack. And the reason for the equations, the reason for the entering the module, the number of teeth, the pressure angle, is now if we edit any of these dimensions, all these variables, we can change everything else. So we can change the module, we can change the number of teeth. And we have to modify these within reason, because some of these edits will just make unrealistic geometry that will just error out. But we can modify and change our tooth profile. And that's it. That's the pinion. Next we're going to work on the rack. Okay, so before we make the rack, let's just recap on what we had to start with. So here is an assembly I made earlier of the rack and pinion. We got a very, very tight tooth profile with no backlash, and it's based on an involute gear profile. So we've already made the pinion or the gear, and now we're going to concentrate in this section on the rack. So we have some base geometry, and we're going to add it to a folder, and we're going to name that pinion. And all this was modeled in the previous section. So we're turning on the sketches that we made previously, and we're turning off the solid geometry, because we're going to use this to help us build our rack tooth profile. So we go to front plane, and we're going to sketch. So the first thing we're going to do is we're just going to create a box. We're going to take a line and going to add some dividing geometry. We're going to take off the vertical constraints, make the centerline construction, make the part symmetrical so we can move these lines around. So then we want to take the line and make it collinear with the center line. Okay, and then we're going to take this geometry down, and we've got what's starting to look like a tooth profile. We need some more geometry, so this is going to be our meshing pitch line. So this line is meshing with the pitch circle. And now we need to construct the root of the tooth, which will be the module times 1.25. So that's the very root of the tooth. And from our imaginary pitch line, we'll create another dimension. This will give us our addendum, which is the module. So it equals a global variable of the module. This gives us 3. So we're looking here at the dedendum and the addendum. We now need to use our pressure angle. So we create another dimension, equal global variables, pressure angle. So if it's confusing where this information is coming from, you need to refer back to the previous section in this tutorial. So let's go tangent, and we've got a meshing gear tooth. Now you might be asking why this isn't an involute. We only need one involute, and that is on the pinion. The rack doesn't tend to be an involute. So now we're just going to create some surrounding geometry. And it's going to become clear why we're doing this very soon. But basically, we're going to create an array in a minute. And this is going to link the various sections of the array to form the rack. So the width is very important. And this is going to be based on the circular pitch. So at the moment we've got an arbitrary dimension of 11.2. We need to replace this with an equation. So this is equals the pitch circle times pi divided by the number of teeth. And this was a global variable, number of teeth, which we input at the top in the equations section. And this works out at 9.42. So we go back into the sketch, and we've got 9.42. So we've transferred that equation into this sketch. So let's just make this root into construction geometry, and now we're ready to extrude. So let's turn on the solid that we had previously, and we're going to match up. We're going to make the rack the same width. So extruded boss, up to surface. We're not going to merge. We're going to go up to this surface, which we just made pink, and we've got a part of our rack. Let's just change it to blue. So we're going to create a linear pattern. There's not going to be any control on this linear pattern, but we need to create something to work with. So linear pattern. We're going to take our direction, and we need some geometry in line. So let's take this line. This is a good line to use. And we'll just leave it as 20 instances. We'll leave the base dimension at 10, although we know it shouldn't be 10. And we're going to, the feature is the solid geometry that we had there. And let's go OK. It's not going to work out. It's not going to link up. But we can fix this by using our control equations. So right click, manage equations. Let's go and find those two dimensions we've just added. So we've got 10 mil and 20 instances. We don't want it to be 10. We want it to match up to that equation we just input, which was 9.42. We can change the number of teeth. So let's add a new global variable. So let's say number of rack teeth, just to give us an extra layer of control as a global variable. We'll make this 30. So the instances, let's change that. We don't input 30. Let's go equals global variable number of rack teeth. OK. So it's alarmed out. So we need to go in and we just need to let it recalculate. So the links have been made. Let's say OK. Something we're not happy with in the geometry. We need to select the right bodies. We don't need to select the circular pattern. Deselect, select the right body. Check everything. Press OK. And you can see that the geometry that we wanted to merge with has merged. Now we've not used the tooth rad, so we're going to add a fillet. Let's make this any value 0.4 again, and we need to pick elements of the rack. So what we've done, we've just gone back in the history to before the pattern, added the rad, gone into equations, find that dimension 0.4, which is going to be very close to the bottom, equal global variables, tooth radius, 0.2. So it's matched up to our global variable you can see at the top. So we've added our fillet, reveal the pattern. It's alarmed out because there's an extra piece of geometry been added. So we select the fillet. Fillet's already selected, but we also need to add the boss extrude. So we've got both features and we've made a pattern out of both features, and that's given us our rack back again. Okay, so the geometry, you can see we've got the geometry. We've got all the base geometry we need. Let's add this to a folder. And at the moment, everything here is modeled in a part. We need to transfer this into assembly, and that we will do in the next section. Okay, so let's start to put together our assembly. We've already modeled in this master template file our rack and our pinion, but it's not going to move. This is a part, and we've basically just created some reference geometry. So we've got two solids, we've got our circular pattern, we've got our linear pattern, and we're going to rename them rack and pinion. There are lots of ways that you can assemble these parts. I'm just going to show you one method. So we're going to delete one of the solids. We're getting rid of the pinion, and that leaves us with the rack. And by doing it this way, I can keep the sketch geometry that was generated, and this gives us something to match up to. So we go File, Save As Rack. This is a new part. So then let's go back into Body Delete, Edit, remove the pinion, and delete the rack. So now the rack goes, and we're left with the pinion. So now we can save this part. Just make sure we turn on the right geometry, because we're going to use this geometry to link up. So File, Save As, we'll name this file Pinion. And we'll save as a copy. Okay, so now we've got two parts to put into an assembly. We now need to start considering starting our assembly. So let's just get rid of this part, File, New, Assembly, and let's find the parts that we've made. So let's add the pinion first. We won't add the rack yet. Let's just constrain this part as we want. So at the moment it's fixed, and that's denoted by the F in the brackets. But we need to make it float. So right-click Float. We've got some geometry for pinning it where we want it. We created an axis earlier, so this is a rotation axis. So let's make this axis to the origin. So we're going to the origin of the assembly, select rotation axis, select, it's a coincidence, and then we'll make the two front planes as so, and that gives us our constraining geometry. So we can rotate this gear or pinion and it's not going to go anywhere. It's constrained in every other direction. So now we'll input the rack. So insert component rack, and we need to constrain again the front planes. This time the front plane of the rack against the assembly front plane, because you don't want it to move. Now we need to match up to the sketch of the pitch circle from the pinion. So before we can use the two top planes to make this happen. So here you can see I've mated the two top planes, and this will cause an intersection between the pitch circle and the corresponding horizontal line on the rack. So let's zoom in, and as I move these parts you can see that that line and the circle are going to interact. So we're going to create some mates now. So let's just mate temporarily with a tangent the teeth in position. This is just to get them in the right position. And we can see everything's meshed. So we just use the tangent mate just to kind of stick things in place. You can see the tangent. Let's turn it off because everything's in position now and we don't want it permanently there. Create an actual mate, and it's going to be a mechanical mate. And there is actually in Solidworks a rack and pinion mate. So we need to pick the pitch diameter, which is the pitch circle. So we pick some geometry. So first we select the pinion gear. Or first we select the rack and we select that equivalent of the pitch circle. And then we go to the pinion and we select that sketch of the pitch circle, and we're basing this around the pinion pitch diameter. which was 96 millimeters. We can reverse this. Let's just check what we've got at the moment. So let's just rotate, move the parts, and they're going in different directions. So we've got the interaction we need, but it's all working in reverse. So we can go back into the rack mate. First turn back on the tangents. This just gives us some kind of control just to get everything back where it was started. Turn the tangent goes off. We go back into the rack and pinion mate and we reverse it. Now let's move the parts again. And let's see what we've got. And that's it. This is the assembly that we started with at the very start as the example in this tutorial. We have a rack and pinion based on an involute tooth profile, and we have no backlash. There's loads of ways you can have backlash. There's some very, very formal ways, and we'll look at this in a backlash in a future video. But for now, here is a working rack and pinion.